Airy's failure was an experiment that proved that the heavenly bodies are in motion, while we are not, using telescopes with water.
Hello, and welcome to I Can Science That. I don't want to get stuck in the rabbit hole that is Flat Earth, but I can't deny the Flat Earth discussion is an excellent source of topics for everyday science. What's more, it is the perfect topic in which to explore the future of science education in modern times. The video clip I just opened with is a clip from a channel called Fight the Flat Earth, and it sparked a discussion. As always, I don't want to get into any debunking here, and I have no intention to try to convince anyone to change their beliefs. Instead, I'd like to provide a more in-depth look into experiments such as Airy's failure and Michelson-Morley, because several people have expressed curiosity about those. So, Professor, what is the deal with Michelson-Morley? Can you science that? Normally, I like to focus on everyday science and experiments that anyone can do at home. The Michelson-Morley experiment isn't really one of those. Don't get me wrong, you can reproduce this experiment yourself. Right here I found a Michelson interferometer you can buy. So you certainly can do this experiment, but it's a little bit expensive for your everyday home scientist. Plenty of universities have these, so it's easy enough to find videos of them. And sometimes lucky students get to see these demonstrations in the classroom. Since I don't expect us to repeat any of these experiments at home, I'm going to structure this video more like a history class. We'll go through the history of science as it applies to this topic, and we'll discuss the results of those experiments and the conclusions that were drawn from them. To start things off, we need to go all the way back to Galileo. This is well before the studies of light speed that we want to focus on, but Galileo provided some key background that's going to come back up again. In 1632, Galileo published a book which contains the first descriptions of what has become known as Galilean Relativity. Galileo's ideas were pretty basic, really, but many people still find this non-intuitive. What we see in this diagram is Galileo riding in a ship at a steady speed where he drops a ball. In the diagram, we see the ball fall from T1 to T2. To him, the ball drops straight down, even though the ship is moving from right to left. In modern times, it's super easy to test this out. You often hear this story playing out on a train, but these days a car seems like the obvious choice. And if you want to take it up a notch, do this on an airplane. I wish I could count on everyone to already understand this, but you don't need to search very hard to find examples on YouTube of people who fail to grasp this. The principle can be described simply as, we don't feel speed, we feel acceleration. If you're in a room blocked off from the view of the outside, you have no way to tell how fast you may or may not be moving. We'll get back to that. For now, we were supposed to talk about experiments with light. Isaac Newton was convinced that light traveled as particles. This was known as the corpuscular theory of light. But there was a lot of debate about that. In 1665, Maria Grimaldi showed that light can diffract, indicating that light appears to be a wave. Then in 1678, Christian Huygens established the wave theory of light. But the situation remained far from resolved. Finally, in 1807, Thomas Young showed that light interferes, and that pretty much settled it. The corpuscular theory was wrong, and we now understood that light is a wave. So, light is a wave. Why do we care? To see why we care, or really why the scientists of the 19th century cared, consider the differences between particle motion and wave motion. Consider this cowboy firing his six-gun while standing on a moving train. The bullet follows the particle model of motion. If you fire a bullet on the ground, the launch velocity of the bullet is v-bullet. But if the cowboy is standing on a moving train, then the cowboy and his gun were already traveling at v-train. That means when we add v-bullet to the speed of the gun, the bullet is now moving at the speed of the bullet plus the speed of the train, relative to the ground. Now let's consider what happens with the sound of the gun firing. Sound follows the wave model of motion. That means the speed of sound does not add to the speed of the moving train. Something that we don't often cover in high school physics class, but seems worth mentioning. If our cowboy fires the gun inside the train, the air will be moving at the speed of the train. The speed of sound is the speed of the pressure wave moving through the medium. So if the medium is moving, it's the speed relative to that medium's speed. As of 1807, the scientific community had established experimentally that light is a wave. And as we've just illustrated, waves need some medium in which to travel. So if light is a wave, what is the medium? Stumped by this question, Huygens proposed that such a medium must exist and called it the luminiferous ether. As far as I can tell, the scientific community accepted this at the time as the only reasonable explanation. You couldn't see it or touch it, but everyone was convinced that there was an invisible medium that light traveled through, and that medium was called the ether. We're going to see that this hypothesis of luminiferous ether ultimately turned out to be incorrect. A series of experiments were conducted that revealed this. Experiments designed to detect our motion through the medium that light waves were traveling through. One experiment that frequently comes up when discussing this topic was in 1871 and has become known as Airy's failure. The theory goes something like this. Imagine the light from a distant star coming towards us through the ether, like this raindrop falling through the air. A telescope is acting like this test tube, catching the raindrop, the photon, at the bottom. But we know the Earth orbits the sun. To imagine the effect that has, let's put our cowboy on the train again and have him try to catch the raindrop. The raindrop is falling down with speed v rain, and the train is moving to the left with speed v train. Relative to the cowboy, that makes the effective velocity of the rain v relative, diagonal. The train represents the motion of the Earth, and the raindrop is a photon traveling through the ether. So now the raindrop hits the side of the test tube instead of going straight down it. To catch the raindrop, we need to tilt the test tube parallel to the relative direction of the rain. Remember that the train represented the orbit of the Earth around the Sun. So 6 months later, the train is going the other way. That would mean the cowboy would have to tilt his test tube the other way to catch the rain. Indeed, we do find that we need to tilt our telescopes very slightly at different times of the year to see the same stars because of this, and we call it stellar aberration. James Bradley had actually figured this much out by 1728 when he was still working with the corpuscular theory of light. Once it was clear that light was a wave and people started talking about the ether, stellar aberration meant that the ether must not be moving with the Earth. Otherwise, this effect wouldn't happen. This brings us to Airy's failure. It was known that light travels slower in water than in air. Airy reasoned, as others had before him, that the presence of the water slowed the light's movement through the ether. He reasoned that this slowdown shouldn't affect the component of the light's velocity caused by the motion of the Earth. As this diagram shows, this would presumably change the angle of the light, or the raindrop, travels through the telescope, the test tube. Airy figured that the angle of the stellar aberration would be different if he filled his telescope with water, and in 1871 he went to some effort to test this. Well, he tested it, but he didn't find what he expected. Airy discovered that the angle of the stellar aberration was exactly the same whether he filled his telescope with water or not. And that is why we call this experiment Airy's failure. The flat Earth community likes to suggest that this is evidence that the Earth is not moving after all. But there are two major flaws in that argument. First, it's extremely obvious now, as it was then, for a multitude of different reasons, that the Earth is orbiting the Sun. Second, this interpretation assumes that Airy and his contemporaries were right about the nature of the luminiferous ether, something we now understand to have been incorrect. When researching for this, I found very little on Airy's failure from mainstream academic sources. The more conspiracy-minded would have you believe this is because we're trying to cover something up. But it seems far more likely that Airy's failure just isn't very interesting to the academic community. Airy wasn't even the first person to attempt this experiment. The Michelson-Morley experiment that followed is far more interesting, so that is the one we covered physics class, and that's the one I'd like to cover next. In 1887, Albert Michelson and Edward Morley conducted a groundbreaking experiment designed to detect the ether wind, the hypothetical difference between the speed of the Earth and the invisible medium that light used to travel through empty space. The Michelson Interferometer is a device that can be used to very precisely measure the wavelength of light. It works like this. A beam of light is split by a half-silvered mirror. Half the light is reflected off the mirror, and half passes straight through. I'm showing here a green arrow for the light that got reflected and a red arrow for the light that passed through, but that's just for clarity in the diagram. It's actually all the same color. The split light beams are then reflected back by full mirrors. The two beams then hit that half-silvered mirror again. The green arrow shows the beam that originally reflected off the mirror returning. Some of that light will pass through the half-silvered mirror. And the red arrow is showing the light that originally passed through. As it returns, some of it is going to be reflected down like this. And here the red and green beams merge back into a single beam of light. Since light is a wave, when those beams combine, they will interfere. That just means we add them together. If the two waves are in phase, this addition doubles the magnitude of the final result. Here we're showing the green wave and the red wave as the two beams combining when they return to the half-silvered mirror. Since they are in phase, the combined beam, shown as blue, is a strong beam of light. On the other hand, the two beams of light could arrive back at the half-silvered mirror out of phase, like this. Now when we add them together, they end up canceling each other out. By sending two beams of light at right angles to each other, Michelson and Morley hoped to detect a variation in the speed of light. They would align one beam parallel to the orbit of the Earth and the other perpendicular. Surely they would see some variation in the speed of the ether. And yet, like Airy, Michelson and Morley were unable to detect any motion in the ether. So did they conclude that the Earth was flat and stationary? No, of course not. The evidence for the motion of the Earth was, and remains, irrefutable. Obviously, it was the ether that became suspect. The ether was a good idea, but the evidence was now in, and the ether turned out to be wrong. And as for the conspiracy cover-up of Airy's failure, what would be the point of hiding that when we're going to specifically cover Michelson-Morley in university physics class? They both had the same results, but Michelson-Morley were far more accurate, and the Michelson interferometer remains an important tool in scientific research today. There can be no doubt that this experiment shocked the scientific community in the late 19th century. We knew light traveled as a wave, but no matter how hard we searched, we couldn't find any motion in the medium the waves traveled through. What could this mean? It took a few more years before Albert Einstein would come along in 1905 and really lay it out for us. The genius of Albert Einstein is beyond question, but with the benefit of hindsight, we can see how all he really did was connect the dots that were already laid out. In 1632, Galileo showed us how all motion was relative, and in 1887, Michelson-Morley showed us that light moved at the same speed no matter how fast the world was moving underneath it. Then, in 1892, Hendrik Lorentz developed the equations describing those findings. What Einstein did was to combine these facts, which had been clearly established, and follow them to their logical, if unintuitive, conclusion. When I learned about special relativity the first time, I somehow missed this connection. That's why I wanted to make this video, to emphasize what I missed the first time around. Michelson-Morley proved that the speed of light is somehow independent of the speed of the observer. Einstein had also taken note of Maxwell's equations. In 1864, even before Michelson-Morley, James Clerk Maxwell discovered that light was an electromagnetic wave, and he was able to calculate the speed of light based on his experiments with electromagnetism. What Einstein saw was that there was no mention of the speeds of the source, the observer, or the medium in these equations. The scientists of the day assumed that the speed Maxwell had calculated had been the speed relative to the medium, but Michelson-Morley had proven this not to be the case. If light moved like a bullet, the speed of light would depend on the speed of the source. If light moved like sound, the speed of light would depend on the medium. Michelson-Morley had shown us that light didn't follow either of these patterns. Faced with this puzzle, Einstein basically doubled down on Galileo's old thoughts about relative motion. Einstein's special relativity simply says, the laws of physics are the same in all inertial frames. And since Maxwell had given us a physical law for the speed of light, that meant the speed of light is the same in all inertial frames. This was precisely what Michelson-Morley and Airy before them had shown us, but Einstein was the first to understand what this meant. Let me pause to point out that an inertial frame just means you aren't accelerating. You can be moving in any straight line at any speed and still be considered in an inertial frame. Einstein imagined a light clock. A light clock is simply a photon bouncing back and forth between two mirrors. Since the speed of light is fixed, the photon should bounce in perfect timing in any inertial frame. But an interesting thing happens when you compare the light clocks from two different inertial frames moving at different speeds. Imagine you're at rest, as far as you can tell, but the other light clock is moving with a steady speed to the right. As far as you can tell, the photon on the other clock is moving diagonally, so it has to travel a lot farther than your clock does on each tick, and that means it must take longer to tick. How much longer? On top, we have the moving light clock with its diagonal photon. On the bottom is the one at rest. Let's call the height of each clock d. We'll say the time it takes the photon to cross that distance on a rest clock is t1. Since we know light moves at a constant speed, traditionally called c, that means d equals ct1. The moving clock is the exact same size, so it is also d tall. But since the photon is moving diagonally, that photon has farther to go than ours, and it'll take longer. Let's call the time it takes the moving clock to tick t2. So the length of the diagonal path is ct2. The moving clock has a steady velocity of v. So in the time it takes that clock to tick once, it will have moved to the right by vt2. We've made a right triangle here, so we'll apply the Pythagorean theorem. I want to find the ratio of t2 to t1. So let's put all the t2's together on the left and all the t1's on the right. A little algebra gets me to t2 over t1 squared. If I factor out the c squared on the right, that gets us to the form you typically see for this equation. We just need to square root it, and there we have the ratio of t2 to t1. That's how much longer it takes the moving clock to tick compared to our stationary one. That was sort of mathy there, but let me repeat. All we did was to say that the speed of light is constant, as Michelson-Morley taught us. Then we did Pythagorean theorem and a little algebra. So far, there's nothing particularly scary about this. The photon in the moving clock takes longer to bounce than our stationary one does. The faster it moves, the slower it ticks. So what? The magic happens when we remember what Galileo taught us. The moving clock is moving at a steady speed. The person holding that clock can't see it moving. To them, it looks as if we are the ones moving steadily to the left at speed v. If the person with the top clock runs these same calculations, they are going to find out that our clock is ticking slower than theirs. If this is the first you're hearing about this, I'm afraid I have hardly done this effect justice. I suggest you take a moment to let that sink in, because it's mind-blowing. Two observers moving at two different speeds perceive each other's clocks to be ticking at different rates. Everybody thinks their own clock is ticking steadily along, like it always has, but anybody moving seems to have a slower clock. So if we pass by each other In separate spaceships, moving in different directions, each of us will look at the other and say, "My goodness, but your clock sure is slow." How can that be? Whose clock is right and whose is wrong? That's really what Einstein was saying. Neither of us is any more right than the other. Every inertial frame is equally valid. The concept of a universal ether against which the speed of light can be measured is false. And he didn't just make it up. It was based on the evidence discovered by those who had come before him, such as Galileo, Maxwell, Michelson, and Morley. I expect some of my viewers are already familiar with the strange effects of relativity, but I'm hoping that somebody out there finds this as surprising as I did when I first heard about this. Maybe you're saying, "No way this is real, this is just a mathematical BS," or as I've once heard, "mythematics." Well, it is pretty hard to imagine, so the first thing I'd want to do is run an experiment to test it. Can you think of an experiment to try this out? Like maybe you'd put a really sensitive clock on an airplane and see if it ends up falling behind because of the speed of the plane. That's exactly what Hafele-Keating did in 1971, and their tests confirmed the equations of special relativity. These days we can do even better. Satellites are much faster than airplanes, and you've probably heard that GPS satellites are designed to accommodate for the time dilation effects of relativity as a matter of routine. If you want more, check out the recent experiments conducted with Europe's Galileo satellites. So yeah, we've verified this. There's one more experiment I wanted to discuss because it often comes up in this same context. This video is already way too long, so let me just mention it briefly. The same folks who claim Airy's failure and Michelson-Morley are evidence for a non-moving Earth often bring up the Sagnac Effect. They'll tell you that the Sagnac Effect shows that Einstein was wrong. The Sagnac Effect starts off similar to the Michelson Interferometer. Light is split by a half-silvered mirror, but this time the two beams are sent all the way around in opposite directions to meet up again and recombine. Once again, we'll be using interference to look for any change in the length of the two paths. This time, since we're sending the light around the same path, we know the paths are the same length. But what we do next is to spin the entire device. One of the light beams is going with the spin, and the other is going against it. Okay, who's ready for a challenge? With what we've learned about relativity, what's going to happen when the beams meet up? Does it take longer for the beam to go around the loop if the loop is rotating away from the beam? What do you say? Can you science that? While you work on that, I'll simply say that the anti-science crowd thinks that the results of this experiment prove Einstein was wrong. It really doesn't. If you understood what we said about relativity and the speed of light, you'll see how this works, and you'll see that the Sagnac effect is precisely predicted by relativity. I'll give you a hint. The speed of light is always a constant in any inertial frame. The Sagnac effect is real, and we use this effect to build the ring laser gyroscopes used in fancy navigation systems. Ring lasers built on this effect are so accurate that they can easily measure the rotation of the Earth. How's that for the ultimate irony? The Sagnac effect is often brought up by people hoping to prove the Earth doesn't move, yet the Sagnac effect can easily prove that it does. All right, so what did we learn? Hopefully we learned a little something about light, relativity, and the history of the discoveries of these things. Michelson-Morley and Airy before them had designed an experiment to detect the motion of the Earth relative to the ether, and they were unable to show any motion at all. Could this mean that the Earth just isn't moving? We're doing science here, and the scientific method tells us that we must set aside our bias and follow the evidence. So let's take this suggestion seriously and give it a fair evaluation. Sure, this could be taken as evidence for a non-moving Earth. When you hear somebody saying, "There's no evidence for a flat, stationary Earth," it's not exactly true, is it? Michelson-Morley could be showing us that the Earth doesn't move, but that would mean that all the other evidence is wrong. I don't want to get into it here, but the evidence for the Earth's orbit and rotation is obvious and irrefutable. In fact, we can include stellar aberration among that evidence. With all the irony that is the human condition, embracing these experiments as evidence for a stationary Earth requires you to accept certain experiments while rejecting others. If Airy's failure is real, then why is Hafele-Keating false? Why is Michelson-Morley genuine, but LIGO is all faked? No, we can't just pick and choose which evidence we like. Reality has to conform to all experimental results, at least everything that can be verified and repeated. That leaves us with no choice but to search for a theory that explains both Michelson-Morley and an Earth that orbits the Sun. Einstein showed us that we needed to give up on the idea of the ether. We'd never found any actual evidence for it. It was just something that seemed like a good idea. Throwing out the ether gave us an explanation for every observation we had at that time, and everything we've learned since. So what about the Sagnac Effect? Doesn't that prove Einstein was wrong? No. The Sagnac Effect is 100% consistent with relativity. It is often claimed otherwise, and Sagnac himself thought so. But as with so many dubious claims, this is the result of misunderstanding what the science actually said. So let me wrap it up with my own take on this. When you have discussions on this topic, you typically get some very closed-minded opinions. These things prove the Earth is stationary. How about, it's got to give you some pause when you realize that none of these scientists ever suggested that. You'll often hear, these experiments in no way show that the Earth is stationary. To be fair, these experiments simply cannot invalidate all the other evidence that demonstrates the motion of the Earth. People say, there's no such thing as the ether. Well, doesn't that depend on exactly how you define ether? What we know for sure is that light doesn't work the way that scientists of the 19th century imagined. Light doesn't need a medium to travel through. I would say the medium for light is the electromagnetic field. It's not a material medium, but that doesn't mean it's not every bit as good as ether. And finally, you can't trust science. It's all a bunch of contradictions and lies. What we have are a lot of really complex details. It's not always easy to figure it out by yourself. But there are people out there who are willing to help you work it out. If you have something you don't understand, or something that looks like a contradiction in mainstream science, find somebody to ask. Feel free to ask me. That's what I'm here for.